That's what that notation is indicating. As x approaches c from the left, as x approaches c from the right, as x approaches negative infinity, as x approaches positive infinity there. All right, let's analyze the basic rational function f of x equals 1 over x. Let's look at its graph and see what's really happening with it. Well, the graph of f of x equals 1 over x is represented in blue here. We can see a couple of things going on. As x approaches negative infinity, in other words, as we go far to the left on the x-axis, it looks like the y-coordinates of this graph are moving upwards closer and closer to a value of 0. In other words, we say the graph of f of x is approaching the x-axis from below the x-axis. All right. As x approaches, it looks like the y-axis from the left, as x approaches 0 from the left, that means we're allowing x to approach the value of 0 coming in from the left. Our function f of x is actually diving down towards negative infinity. All right, or the y-coordinates are getting smaller and smaller and smaller on this graph. Let's go on the other side of the y-axis. As x approaches 0 from the right, in other words, as we move in towards the y-axis from the right, the points on this graph are blowing up or moving upwards towards positive infinity. So f of x is approaching positive infinity as x approaches 0 from the right. And finally, as x approaches positive infinity, we go far to the right on the x-axis. We can see that the y-coordinates of the points on this graph are getting closer and closer to 0. Or we say that f of x is approaching the x-axis or approaching 0 from above the x-axis. All right. And so that's what's going on with the analysis of this rational function here. Notice the graph will never touch the x-axis, no matter how far to the left you go on the x-axis or how far to the right you go. And also, it appears that the graph of this rational function will never touch or cross the y-axis. Okay, as we're going to find out, the horizontal axis, the x-axis, is referred to as a horizontal asymptote to the graph of this rational function, and the y-axis is referred to as a vertical asymptote. These tables here are just indicating how we're moving with x. In other words, as x approaches negative infinity, they put smaller and smaller values into the function f of x equals 1 over x, and you can see that f of x is actually approaching 0, but approaching 0 from the negative side, or we say f of x is approaching 0 from below 0. Okay. And this table over here in the upper right corner is saying as x approaches 0 from the right. Okay, as x approaches 0 from the right, in other words, as we get closer and closer to 0, albeit coming in from the right, the values of f of x are actually blowing up towards positive infinity. This lower left corner table is saying as x approaches 0 from the left, as x is moving in from the left towards the y-axis, the values of this function are diving down towards negative infinity. Finally, the lower right corner table indicates as x approaches positive infinity, f of x is actually getting smaller and smaller and smaller and actually approaching 0, but approaching 0 from the positive side of 0, not the negative side. Okay, any questions about these tables here or this graph of this rational function? Okay. All right, let's look over example 1 here. The graph of f of x is equal to 1 over x squared is under the microscope. This is a rational function. And notice that they have already graphed this function here for us, which is nice. We're going to analyze this graph as we allow x to approach various things. In A, as x approaches negative infinity, in other words, if I go far to the left on the x-axis, it appears that the graph is diving down towards the x-axis from above the x-axis. So we would say that f of x is approaching 0 from what direction? f of x is approaching 0 from above or from below. What's going on as x approaches negative infinity? It looks like f of x is approaching the x-axis, excuse me, from above, correct? And so technically for a here, we would say that f of x is approaching 0. And technically it is approaching 0, not just approaching 0, but it's approaching 0 from the positive side of 0, from above the x-axis. As x approaches 0 from the left, in other words, as we allow x's values to get closer and closer to 0, albeit coming from the left, we can see that the points on this graph are moving up very rapidly towards positive infinity. So as x approaches 0 from the left, f of x is approaching infinity. Going on the other side of the y-axis and allowing x to approach 0 from the right, we see also that this graph is going up towards positive infinity. As x approaches positive infinity, we go far to the right on the x-axis. We see the graph is diving down towards the x-axis. So again, f of x is approaching 0. Any questions about the analysis with this graph here and the symbolism being used here? All right. Okay, so classwork number 1, ladies and gentlemen, what I want you to do is I want you to complete this problem here using the graph of this rational function, 1 over x minus 2. I would like you to complete this this notation here, A through D. Go ahead and do that using the graph, okay? Try not to peek at the answers. Let's see what's happening here. So I'll give you about a minute to do this, okay? No more than a minute. All right, so A, as x approaches negative infinity, as we go far to the left on the x-axis, notice the graph is approaching the x-axis from below the x-axis, so we say f of x is approaching 0. B, as x approaches 2 from the left, this vertical black dashed line going through the x-axis at 2, as x approaches 2 from the left, approaches that vertical dashed line from the left, we see our graph is diving down towards negative infinity. As x approaches positive 2 from the right, as we come in towards that vertical dashed line from the right, the graph is blowing up towards positive infinity. And finally, as we have x approach positive infinity, go far to the right on the x-axis, the graph is diving down towards the x-axis from above the x-axis. So we say f of x is approaching 0, technically from above. Okay. All right. Okay, this is the definition of a vertical asymptote. We say, ladies and gentlemen, that a line x equals c, a vertical line x equals c, is a vertical asymptote of the graph of a function f if f of x approaches infinity or negative infinity as x approaches c from either side. In other words, we would call this vertical pink dashed line that goes to the x-axis at c, we would call it a vertical asymptote, and its equation would be x equals c. If as x approaches this line, vertical dashed line from the left, in other words, as x approaches c from the left, f of x approaches positive infinity, or as x approaches c from the left, f of x dives down towards negative infinity, or as x approaches c from the right, f of x either approaches positive infinity or negative infinity. If that's the case, then we would classify x equals c, that vertical line, as being a vertical asymptote to the graph of our rational function. Or we would say the rational function is asymptotic with respect to that line x equals c. All right, where do vertical asymptotes hang out now that we know that, what they look like and what the characteristic is? Well, they hang out, ladies and gentlemen, where the denominator of a rational function is equal to 0. In other words, wherever a rational function is undefined is where you're going to find vertical asymptotes. And therefore, in order to locate vertical asymptotes, we take the denominator of our rational function and we set it equal to 0, and then solve for x to determine where these vertical asymptotes hang out. All right, let's go over exercise example 2. Here's a rational function, f of x equals 2 over x minus 3. I have a question, ladies and gentlemen. Where would the vertical asymptote for this rational function hang out? Well, it's going to hang out where the denominator is equal to 0. So if you take x minus 3 and set it equal to 0, and then solve for x, you'll discover that a vertical asymptote for this rational function will exist at x equals positive 3. And sure enough, if you were to take the time and graph this rational function, you can see that behavior that was mentioned in the definition above as to why x equals 3 qualifies as being a vertical asymptote. Because as x approaches 3 from the left, f of x dives down to negative infinity. As x approaches 3 from the right, f of x moves up towards positive infinity. Now for the rational function in B, g of x, this denominator here, in order to locate vertical asymptotes, the denominator should be set equal to 0. And then setting that denominator equal to 0, that's where your function is going to be undefined, we would have to solve the resultant equation. Well, it's a lot easier to solve if you first factor this trinomial into the product of these two binomials. And then setting these binomials equal to 0, we discover that there's two vertical asymptotes for this rational function. They hang out at x equals 1/3 and also x equals -2. And sure enough, if you were to graph this rational function, you can see that that's precisely where our function is undefined and where the graph either dives down towards negative infinity or up towards positive infinity as you approach these vertical asymptotes from the left and the right. Okay, and notice the graphs will never touch or cross a vertical asymptote anywhere. Reason being is because it's at those values or places where your rational function is undefined. Okay, any questions how we're locating vertical asymptotes here so far? Finally, go ahead.
So you can think of them as sort of like restrictions in a way.
Yes, yeah, exactly. You can think of them as being like restrictions on a rational expression that we looked at in the way, further back. Where you have restrictions is where your vertical asymptotes hang out. Exactly. That's another way of thinking about it. All right, how about this rational function here, 4x squared over x squared plus 4? Notice this denominator, think about it, would never, ever be equal to 0. No matter what you put in for x, ladies and gentlemen, you will never be able to square any number and ever generate -4, such that that would cause this denominator to be 0. So for that reason, this rational function here does not have a vertical asymptote. And so that also answers a more general question. Do rational functions always have a vertical asymptote? The answer is no. Here's a classic example in C here. All right, you can clearly see that nowhere as x approaches any vertical line from the left or the right does our graph move up towards positive or negative infinity. That's why there is no vertical asymptote for this rational function k of x. All righty. Okay. All right, now I want to go over this function here. This is an interesting one here. Let's look at this rational function. 2x squared plus 5x plus 3 over x plus 1. Now, it would appear that there's a vertical asymptote at x equals -1, correct? But stay tuned on that one. If I was to factor this numerator, this trinomial, I'm not going to show the factorization of that because that's a waste of time. We know how to factor these trinomials. we get this right here. Now, ladies and gentlemen, notice something interesting happens here. The x plus 1 factors drop out between the numerator and the denominator. So in essence, what's going on here is when you drop the x plus 1s out between the top and the bottom, our rational function actually collapses down to, in a sense, a linear function. Okay. And so what's going on here? We know that the function is not defined at -1, right? Because your denominator here would go to 0. So x, a restriction you would place on this denominator to force this to be defined is to say that x could never be equal to -1. So what's going on at -1? Well, if you were to graph this linear function at x equals -1, ladies and gentlemen, you are not going to have a vertical asymptote. Okay. At x equals -1, you're going to have what's called a hole in the graph. A hole in the graph is what you're going to have. Not a vertical asymptote, but a hole in the graph. And your author in your textbook has graphed this rational function. And let's go take a look at the graph of that. And you can see the graph of that rational function is right here in blue. Okay. We got to be careful because just because our function is not defined at x equals -1, we cannot necessarily say, and in fact, in this case, we cannot say that we have a vertical asymptote at x equals -1. Because this factor of x plus 1 drops out with the factor of x plus 1 in the numerator, we have to conclude that we don't have a vertical asymptote at x equals -1. We have a hole in the graph at x equals -1. The function is not defined at x equals -1, but it's not a vertical asymptote. Okay, it's just a hole in the graph. So you got to be a little bit careful. All right, don't think that where your denominator of your rational function is always equal to 0, you're always going to have a vertical asymptote. Sometimes you might have a hole in your graph. So how are we going to know the difference? Well, I'll tell you how you know the difference. The difference is if you come back up to this one right here, notice for this function g of x, we did have vertical asymptotes at 1/3 and -2. Why? The reason is because none of these factors in the denominator cancel out with any of these factors in the numerator. We're stuck with these denominator factors. And because of that, you have vertical asymptotes there. But if you can ever cancel out any factor in the denominator with a factor in the numerator, then the vertical asymptote ceases to exist there, and you actually have instead a hole in the graph. Okay? So does that make sense there? Any questions about that? All right. So just be careful with that. And that's why in this purple shaded box, it's entitled Avoiding Mistakes. We got to be careful in this case to think that there's not a vertical asymptote at x equals -1, but rather a hole in the graph. Right? The function is undefined at x equals -1. Now, in calculus 1, when you talk about the continuity of a function on various intervals, you'll learn that we have what's called a removable point of discontinuity at x equals -1. Just by redefining this function, you could close that open hole. And once you close it, then the function will be continuous also at x equals -1. So this is called a removable point of discontinuity. Now, anywhere you have a vertical asymptote, those are always classified as being non-removable points of discontinuity. Okay. Vertical asymptotes, you can never remove the discontinuity by redefining your function. But when you have holes in your graph, you can remove the discontinuity by simply redefining your function. For instance, I could say let f of x be equal to 2x plus 3 for all x not equal to -1. And then I could specify let f of x be equal to +1 when x is equal to -1. That would close this open hole and therefore remove that point of discontinuity. Okay. All right. Okay. Now, ladies and gentlemen, what's a horizontal asymptote? All right. Well, here's the definition of a horizontal asymptote. A horizontal line whose equation would be y equal to d, or d is just some number on the y-axis, is classified to be a horizontal asymptote if as x approaches negative infinity, if f of x approaches that horizontal line from above or from below, or as x approaches positive infinity, the graph f of x approaches that horizontal line from above or from below. If your function's graph exhibits this characteristics for very small or very large values of x, we would therefore classify this horizontal line, this horizontal pink line, as being a horizontal asymptote to the graph of your function. Now, unlike vertical asymptotes where your graph can never cross a vertical asymptote, never cross or touch a vertical asymptote, ladies and gentlemen, graphs can intersect or cross a horizontal asymptote. But the definition of a horizontal asymptote only comes into legitimacy or existence for very large values of x or very small values of x. In which case, so my point is this, your graph could maybe cross this horizontal asymptote like right here, but as you continue to go farther and farther to the right of the x-axis, this graph then would have to settle down and start becoming asymptotic with respect to that red line, and it will never ever cross or touch it again, okay? That also holds true for as x approaches negative infinity. This graph would have to turn around somewhere down in here and have to become asymptotic or approach that red horizontal line, never to ever touch it or cross it again. But your graph could cross somewhere in between, okay? It can happen with horizontal asymptotes. All right. So how do we locate where horizontal asymptotes occur? We know what the graph of a rational function is going to look like in their vicinity for large or small values of x. Well, how do we locate them? Well, this is how you locate where a horizontal asymptote hangs out. There's three possible scenarios. Suppose that we have a rational function where we have an nth degree polynomial divided by an mth degree polynomial. All right. Well, there's three situations or cases here. Number one, suppose that the degree of the numerator polynomial n is greater than the degree of the denominator polynomial. If that's the case, ladies and gentlemen, we would say that the rational function f of x would then have no horizontal asymptote. There would be no horizontal asymptote for such a function. If, on the other hand, the numerator degree is less than the denominator degree, like if you have a second degree polynomial over like a third or fourth degree polynomial, then your horizontal asymptote will exist, and it will be the line represented by the equation y equals 0. But the horizontal line represented by the equation y equals 0 is nothing more than the x-axis. So if the numerator degree of a rational function is less than the denominator degree, the x-axis will always be a horizontal asymptote. One last scenario. What if the degrees are the same? What if we have like a third degree polynomial over a third degree polynomial? Well, in that case, we will have a horizontal asymptote, the equation of which will be equal to the ratio of the leading coefficients of the numerator and denominator polynomials. In other words, the horizontal asymptotic equation would be y equal to a sub n divided by b sub n, where a sub n is the leading coefficient of the numerator polynomial, b sub n being the leading coefficient of the denominator polynomial. So there's three possible scenarios as to whether or not you do have a horizontal asymptote, and if so, what the equation would be and where it would hang out. Any questions about this definition of the location of a horizontal asymptote? Okay. All right, example 3. So, ladies and gentlemen, let's take a look. This rational function in example 3, part A, would it have a horizontal asymptote? And if it does, what would be its equation? Where would it hang out? Well, notice the numerator degree is of degree 2 and the denominator degree is of degree 4. What was the case if the numerator degree was less than the denominator degree? Do we remember?
Y equals 0.
Yeah, it's going to be the x-axis would be the horizontal asymptote. So therefore, the horizontal asymptote for this rational function in 3a literally is going to be the horizontal asymptote. And if we take the look at the graph of this rational function, sure enough, you can see that the x-axis, which is y equals 0, is indeed the horizontal asymptote to the graph of f of x, in the sense that as x approaches negative infinity, the graph is approaching that horizontal line from above, and as x approaches positive infinity, the graph is also approaching that line, albeit from above. That's why we call this a horizontal asymptote. Okay. Notice it does not appear that the graph of f of x is ever going to cross or intersect or touch this horizontal asymptote, and because if it did, they would have showed that point of intersection. So there is no place where this graph will ever touch or cross that horizontal asymptote. All right, we'll show you, if it does, how to locate that point of intersection. All right, how about B here? Notice we have a third degree polynomial divided by a second degree polynomial. And because the numerator degree exceeds that of the degree of the denominator, what would we expect? Well, if the numerator degree is greater than the denominator degree, then there would be no horizontal asymptote. So this function does not have a horizontal asymptote. And you can see by the graph of B, g of x, you can see that there is no horizontal asymptote, because as x approaches positive infinity or as x approaches negative infinity, the graph never does settle down and approach a horizontal line anywhere. There's no horizontal asymptote here. Okay. One last scenario is look at h, function h of x. The numerator degree is equal to the denominator degree. They're both quadratic polynomials. Because of that, the horizontal asymptote will be the line y equal to the ratio of the leading coefficients. It's going to be this case right here. So therefore, the equation of the horizontal asymptote for the function in C is going to be y equals 8 divided by 2, or y is equal to 4. So the horizontal line y equals 4 is a horizontal asymptote to the graph of h of x. And you can see as x approaches negative or positive infinity, the graph indeed does become asymptotic with respect to the horizontal line. In other words, approaches it closer and closer and closer, but will never touch or cross it. Notice something interesting happens here. Notice the graph does cross the horizontal asymptote right here. So it does cross right here, but then as we go further to the right on the x-axis, the graph then turns around and then approaches that horizontal asymptote, never to touch or cross it ever again. All right. So I have a question for you, ladies and gentlemen. How do we know this point of intersection between the graph and the horizontal asymptote? How would we find where this graph crosses that horizontal asymptote? Well, we know the equation of a horizontal asymptote is y equals 4. So if I set h of x here in this rational function equal to 4 and solve this equation for x, I would be able to determine precisely where this point of intersection occurs. So let's see if we can do that. I'm going to set h of x. I'm going to set h of x here equal to 4, because again, that's the equation of my horizontal asymptote, y equals 4. And then we're going to have to solve this equation. So let's go ahead and see if we can do that quickly here. This will, if nothing else, give us practice in solving a quadratic equation. So what I'm going to do is I'm going to set that rational function equal to 4. Now I got to solve for x. I'm going to multiply both sides by this denominator here, clear this fraction out on the left side, in which case I will have 8x squared plus 9x minus 5 equal to 4 times 2x squared plus 1. Distributing the 2 inside the parentheses, I have 8x squared plus 9x minus 5 is equal to 8x squared plus 4. And now I want to solve this quadratic equation. Well, actually, in essence, it is going to cease to be a quadratic equation. Why? Because when I subtract 8x squared from both sides, we can see that 8x squared drops out on both sides of our equation. And our messy quadratic equation collapses down to an ordinary first degree or linear equation. And now we just solve for x. Adding 5 to both sides, we get 9x equals 9. Divide by 9, and we discover that x is equal to positive 1. Putting positive 1 back into our rational function here for x here, here, and here. We'll crank out the y coordinate. So we're gonna have 8 times 1 squared plus 9 times 1 minus 5. And that's all gonna be divided by 2 times 1 squared plus 1. So this is going to be 8 plus 9 is 17 minus 5 is 12. And this is going to be 2 plus 1 is 3. So you can see, ladies and gentlemen, that the point of intersection between the graph of this rational function and the horizontal asymptote y equals 4 is going to occur when x is equal to 1 and y is equal to 4. So that is the point of intersection. That is the point of intersection between the graph and the horizontal asymptote. So again, to find the point of intersection between the graph of a rational function and the horizontal asymptote, set the rational function equal to what the horizontal asymptote is, and then solve for x. So let's go back and convince ourselves that yes, it does appear that 1, 4 is exactly the point of intersection between the graph and the horizontal asymptote. Any questions how we found that point of intersection? All right. Ladies and gentlemen, there is one other type of, well, I'll tell you what, we could do this, we'll call this classwork number 2 here. I want you to do skill practice problems 3, A, B, and C. I just want you to indicate to me whether the rational function has a horizontal asymptote, and if it does, what would be its equation? Okay, go ahead. I'll give you a minute or so for skill practice 3, A, B, and C. All right, for A, notice the degrees of both the numerator and denominator are the same. They're both second degree polynomials. Therefore, the equation of your horizontal asymptote would be y equal to the ratio of the leading coefficients. So y would be equal to 7/4. It would be that horizontal line, y equals 7/4. That would be your horizontal asymptote. For B, the degree of the numerator is greater than the degree of the denominator. And in this case, because of that, there would be no horizontal asymptote for m of x. Finally, in case C, the degree of the numerator is of 0 degree, being a constant. The degree of the denominator is 2. Since the degree of the numerator polynomial is less than the degree of the denominator, we discover that the horizontal asymptote would be the x-axis. Y equals 0 would be its equation. Did we all get those correct there? All right. All right, there is one other type of asymptote, ladies and gentlemen, that we could run into from time to time. It is called a slant asymptote, okay? A slant asymptote, as the name suggests, is going to be a slanted line that your graph will approach but never cross or never touch. And if you look at this rational function, f of x equals x squared plus 1 over x minus 1, we see that we do have a slant asymptote, this pink slanted dashed line that qualifies as being a slant asymptote, and its equation is y equals to x plus 1. How do we find the equation of a slant asymptote? Well, it's pretty simple. you have to just literally divide the denominator into the numerator by performing either long polynomial division or using synthetic division, okay? And so therefore, to find the slant asymptotes equation y equals x plus 1, we would have to divide x minus 1 into x squared plus 1. Now, your author has illustrated it being done two ways. First, long polynomial division, where they divided x minus 1 into x squared plus 1. And notice they did get a remainder of 2 after performing that long division. But ladies and gentlemen, the remainder does not play into the equation of a slant asymptote. The reason being is because slant asymptotes become realized in their nature as x approaches positive or negative infinity, in which case the remainder portion just drops out of the picture. It drops out to 0 anyways. So we're only concerned in the non-remainder portion after we divide the bottom into the top to determine the equation of a slant asymptote, y equals x plus 1. And notice they also divided positive 1 synthetically into the coefficients of x squared plus 1 to also give us the same result. Now, how do we know when a slant asymptote for a rational function exists? How do we know that these functions even have a slant asymptote? Well, here's how. A rational function will have a slant asymptote if the degree of the numerator is exactly 1 greater than the degree of the denominator. So notice the degree of this numerator is of degree 2, and the degree of the denominator polynomial is 1. Because the numerator degree is exactly 1 larger than the denominator degree, we would say that this rational function does not have a horizontal asymptote, but it does have a slant asymptote. And again, this is how you find the equation, by dividing the bottom into the top. Any questions how they found that slant asymptote equation by using long polynomial division or synthetic division? So if you graph that line, y equals x plus 1, you'll see that the graph of your rational function will approach that line for extreme values of x, but never cross or touch it. Okay. Okay. Here's another one, ladies and gentlemen, that you might want to take time to look at. Here's a rational function in example 5, the degree of which is 2, the denominator degree is which is 1. Because the numerator degree is 1 larger than the denominator degree, this rational function would have a slant asymptote. It also possesses a vertical asymptote at x equals 2. How do I know I have a vertical? How do I know I have a vertical asymptote at x equals 2 and I don't have a hole in my graph? Can anybody explain that to us? How do I know at x equals 2 I have a vertical asymptote and not a hole in my graph?
When you factor it, it doesn't come out to one of them being x minus 2.
Yeah, exactly. Notice this x minus 2 factor in the denominator does not cancel with any factor in the numerator. Because of that, we don't have a hole in our graph at x equals 2. We have a vertical asymptote at x equals 2. And that, like I said earlier, is called a non-removable area of discontinuity at x equals 2. There would be no horizontal asymptote because the numerator degree is larger than the denominator degree. But because the numerator degree exceeds that of the degree of the denominator precisely by 1, there would be a slant asymptote. And to find it, you literally divide the denominator into the numerator. Now you can do this one of two ways. You can either do it using long polynomial division, or you can use synthetic division. Wait a minute. Yeah, you can use synthetic division also. So the equation of the slant asymptote is just y equal to 2x minus 1. That is it. And notice that they graphed y equals 2x minus 1. That is the slant asymptote. And this rational functions graph is asymptotic with respect to it, as x becomes very small and x becomes very large. Okay. And notice the location of the vertical asymptote, x equals 2. And notice there's no horizontal asymptote. All right. Is this making any sense here? I know it seems kind of like a lot, but there's quite a bit that goes into rational functions. All right. So how do we graph rational functions? By the way, I want you, well, we could maybe go over this quickly here. One way to graph rational functions is if you can feed off of the basic parent function 1 over x, and use your knowledge of transformations of functions. That is a very convenient way to graph a more complicated rational function. Notice, ladies and gentlemen, the parent function for this rational function would be f of x equals 1 over x. And can anybody explain to me what has happened to the graph of y equals 1 over x to get the graph of this more complicated rational function? What does this x plus 2 signify? What type of transformation has occurred for the basic rational function 1 over x? If I got x plus 2 here. In other words, if I form a new function called f of x plus 2, what happens to the graph? Do you remember?
Shift left 2.
Yes, so the graph gets shifted to, oh, by the way, I said that wrong. The basic parent function is not 1 over x. The basic parent function is 1 over x squared. I do apologize for that. And the graph of f of x equals at 1 over x squared would be the graph in gray here. Can you see it there? All right, so if you form a new function, which is f of x plus 2, that causes the gray graph to be shifted 2 units to the left. So notice the vertical asymptote, which is the y-axis, shifts 2 units to the left also. So now the vertical asymptote becomes x equals -2, which makes sense. You would have a vertical asymptote at x equals -2 because that's when this denominator would be equal to 0 at x equals -2. All right. Notice adding 3 to your function causes the function's graph to be shifted upwards, what? 3 units, correct? So what originally was the horizontal asymptote, which was the x-axis, now gets shifted upwards 2 units. So now the horizontal axis gets shifted up to what? Horizontal asymptote now becomes a horizontal line y equals 3, because the blue graph got shifted upwards 3 units. And then finally, the green graph would be the graph of this rational function right here, f of x. So sometimes by using transformations from the basic parent function's graph, that is a effective way to graph the rational function. Talk to me quickly, what would happen to the graph of f of x equals 1 over x if I wanted to graph this rational function? What does x minus 3 cause the graph to do? Be shifted how? X minus 3. F of x minus 3 causes the graph to do what? It would be shifted
3 units to the right.
3 to the right, and then subtracting 2 off from a function causes the graph to go down 2 units, right? So if you think of the graph of f of x equals 1 over x, where the y-axis was a vertical asymptote, the x-axis was a horizontal asymptote, notice both those asymptotes get shifted 3 to the right and then down 2 units. And so now you would have the graph of this new function called g of x. So transformations, still can come into play and enable you to effectively graph rational functions. Unfortunately, we cannot use transformations for all rational functions, though, as some are kind of complicated and the parent function is really unknown. All right. So in general, how do we graph rational functions? Well, this is on page 354 in your textbook in this purple shaded box. We've discovered pretty quickly that in this textbook, anything in a purple shaded or outlined box is pretty important. It's either a very important definition or theorem, or it contains some sort of an algorithmic way of doing something. All right, so how do we graph rational functions in general? This is the things you want to consider in this order. First of all, you want to try to find any y-intercept. Does the function have any y-intercept? You find that by letting x be 0. Number 2, does your rational function have any x-intercepts? You find those by setting y, which is really called normally functional notation, you set that equal to 0. Number 3, identify vertical asymptotes. Does your rational function have vertical asymptotes? And locate them on the graph as dashed vertical lines. Number 4, does your rational function have any horizontal asymptotes? Or maybe a slant asymptote, or neither? If it does have a horizontal or slant asymptote, please represent those as dashed lines. Number 5, if your graph has a horizontal asymptote, where does it cross the horizontal asymptote? Okay, and to find out the point of intersection, you just set your irrational function equal to the value of your horizontal asymptote. Number 6, you can use your knowledge of symmetry, whether a function is even or odd symmetric with respect to the y-axis or the origins. That can also aid your ability to graph rational functions. Number 7 is very important. It says plot at least one point on the intervals defined by, and here's how these intervals are always going to be defined. They're going to be defined by x-intercepts, vertical asymptotes, and any points where the function crosses the horizontal or slant asymptote. And then from there, we can then sketch our graph. Okay. So here we go. What I'm going to do is I'm going to apply all that knowledge to example number 7 and show ourselves how to go about graphing this rational function here. And well, your author pretty much lays it all out here. It's all laid out. So I guess we'll maybe just walk down through this one here. All right. What's the first thing we should look for? Does our rational function have a what? A y-intercept. Okay. How do we find y-intercepts? We let x be what? 0. So what did they do? They evaluated their function at 0 to try to find where your y-intercept is. Let x be 0, and they find out your y-intercept is -1.5 or -3/2. That's your y-intercept. That's where the graph's going to go through the y-axis at that point. Number 2, are there any x-intercepts? To find x-intercepts, we set y, or in this case, f of x equal to 0. In other words, we set our rational function equal to 0, and then we have to solve this equation for x. How would I solve this for x, this equation? They're leaving out a step. What step did they leave out? Anybody? How do you solve this equation for x? Right here. Well, we'd like to get rid of this fraction on the left side by multiplying both sides by what? What would we multiply both sides by?
X minus 2.
X minus 2. And when you do that, the x minus 2 drops on the left and would still have 0 on the right. So therefore, the equation collapses down to x plus 3 equals 0, which means we have one x-intercept. And that occurs at x equals -3, 0. That's your only x-intercept. That's where the graph is going to cross your x-axis or touch your x-axis, depending upon the multiplicity of x plus 3. But since x plus 3 is a multiplicity of 1, the graph will cross through the x-axis at -3, 0, correct? All right, what's next? We found the y-intercept, found the x-intercept. Any vertical asymptotes? Well, vertical asymptotes, again, occur where the function is undefined. And in this case, will occur where x minus 2 is equal to 0. So set x minus 2 equal to 0 and solve for x. We can see that the vertical asymptote occurs at x equals 2. That would be your vertical asymptote. And we know it's not a hole in the graph at x equals 2 because we cannot cancel this factor x minus 2 out with any factor in the numerator. So that's where your vertical asymptote occurs. We would plot that as a vertical dashed line in our xy plane. X equals 2. You see that there? They graph the vertical asymptote as x equals 2 there. All right, what else? After a vertical asymptote, number 4, are there any horizontal asymptotes? Well, we have to compare the degrees of the numerator and denominator polynomials to determine where, if any, horizontal asymptotes hang out. Notice both numerator and denominator polynomials are of degree 1, and since the degrees are equal, the horizontal asymptotic line is going to be y equal to the ratio of the leading coefficient. So y is equal to 1 over 1, or y would be equal to 1. So your equation of your horizontal asymptote is y equal to 1. You would then plot that as a horizontal dashed line in your xy plane. And notice there it is, y equals 1 is plotted as a horizontal dashed line. There's your horizontal asymptote. What else here? Well, if we do have a horizontal asymptote, we want to determine where the function crosses the horizontal asymptote. And to determine that, since we know the equation is y equals 1, we set our rational function f of x equal to 1. So we have to set x plus 3 over x minus 2 equal to 1 to determine where, if any place, our graph crosses the horizontal asymptote. Now, to solve this equation, you would multiply both sides of this rational equation by x minus 2, and you would end up with this linear equation. But something interesting occurs. Notice when you try to solve for x by subtracting x from both sides, x drops out on both sides and leaves us with a false numeric statement. That would indicate that this equation has no solution when you set it equal to 1. That indicates there is no point in which our graph crosses the horizontal asymptote. It will not cross it anywhere. Okay. Symmetry, you can maybe get into that. If you put negative x in for x everywhere and try to simplify your function, you'll discover that f of negative x is neither equal to f of x or neither equal to negative f of x. So the graph is not symmetric with respect to the y-axis or the origin. In other words, it's not an even or odd function. Last but not least, les amis, we want to plot at least one point that occurs in each of these intervals, and the intervals are defined by what? You remember how the intervals are defined? Step number 7. It says plot at least one point in the intervals defined by the x-intercepts, the vertical asymptotes, and any point of intersection between the graph and the horizontal or slant asymptote. Well, our intervals of interest are going to be formed by the x-intercept, which is -3, and also the vertical asymptote, x equals 2. So we do have 3 intervals of which to compute at least one point that lies on the graph of this rational function. And how can we do that? Well, give me a nice value that's less than -3. Your author chose -4. Your author then put -4 into your rational function, put -4 in for x here and here, and discovered that f of -4 would give you -1 over -6 or positive 1/6. So therefore, we would have a point on our graph in this interval that is going to be at -4, 1/6. My question is this: would that point in this interval be below or above the horizontal asymptote? That's very important. Where would this point -4, 1/6 be? Below or above the horizontal asymptote in this interval here? Well, the horizontal asymptote was y equals to 1, and 1/6 is less than 1. So that point's going to be below the horizontal asymptote here. So will my graph ever cross the horizontal asymptote? The answer is no. In fact, why did this point have to be below the horizontal asymptote? Well, because we know the x-intercept is -3, and we know the y-intercept is this point here. The graph has to contain these intercepts. So it's imperative that at x equals -4, or for any point in this interval, that the y-coordinate be below 1, because the graph cannot cross the horizontal asymptote. Because if it crossed the horizontal asymptote, we would have discovered that back over here. Do you agree? By having set our equation equal to 1, we would have found that point of intersection. But there is no point where the graph crosses the horizontal asymptote. That's why it's this point -4, 1/6 has to be below the horizontal asymptote. Now, we don't have to worry about plotting a point in this interval from -3 to 2 because we already have the y-intercept plotted. Finally, we want to find at least one point that lies in this interval from 2 to infinity. And your author chose to pick +2. Put 2 into your rational function for x. So f of 2 is going to be 2 plus 3 over 2 minus 2. Wait a minute, what did they pick?
3.
I'm sorry, they picked 3. My bad. They picked +3 in this interval to the right. They put 3 in. And that would be 3 plus 3 over 3 minus 2, which would be 6 over 1, or 6. And so the point 3,6 would lie where? Now, does the point 3,6 lie below this horizontal asymptote or above 3,6? 3,6. It lies above the horizontal asymptote. So therefore, we can sketch the graph now. We know enough about this. We start from left and work to the right. We had our point -4, 1,6, which is going to be like right here. So our graph is going to be asymptotic with respect to this horizontal axis. So as x approaches negative infinity, the graph is going to approach the horizontal axis, never to cross or touch it. And then the graph will come down, pick up the x-intercept, pick up the y-intercept. It will have to dive down then towards negative infinity as x approaches the vertical asymptote from the left. It's got no choice but to dive down. How do I know my graph cannot turn around and cross the x-axis again? How do I know it can't turn around somewhere in here and go across the x-axis? Because if it could, we would have found the x-intercept up there when we found the x-intercepts. There is no other x-intercept except -3. So the graph cannot cross. It cannot turn around here. It has no choice but to dive down towards negative infinity and approach this vertical asymptote from the left. Finally, as we go to the right of the vertical asymptote, how do I know my graph does not occur down in here? There's no graph down in here. Well, because remember, we plotted a point in this interval, which is 3, 6, and 3, 6 is above this horizontal asymptote. So the rightmost branch of this graph has to be above the horizontal asymptote. So as x approaches 2 from the right, the graph has to move up towards positive infinity. And as x approaches positive infinity, the graph has to dive down and approach this horizontal asymptote, never to touch or cross it. And ladies and gentlemen, based on all that analysis, we can then sketch the graph. Everybody understand that? How we did that? I know it seems like a lot, but I went over that in detail, and that's why it killed a lot of time. All right. In reality, you'll probably fly through most of these steps quite quickly. Okay. All right. Okay. We're going to look at one now. I'm going to walk through another one here, but this one we're going to kind of work out here. Suppose that I want to graph or sketch a graph of f of x equal to 4x over x squared minus 4. So to do this, to sketch the graph, we're going to have to learn more about this rational function here. All right. Notice we cannot play off of a basic parent function and use transformations to graph this because our basic parent function is not 1 over x squared because we got an x up here. So this one here, we're just going to have to find out all the information indicated in that table there. Number one, any y-intercept. How do we find a y-intercept? We let x be 0. That's to say that our y-intercept is going to be f of 0, which means it's going to be 4 times 0 over 0 squared minus 4, which is going to be 0. My y-intercept is the origin, 0, 0. That's my y-intercept. How about x-intercepts? Any x-intercept or seps? To find out, we let y be 0. Well, it's not called 0. It's not called y. It's called f of x. But we said f of x equals 0, which means that now we're having to solve this rational equation. And ladies and gentlemen, if I was to solve this equation for x by multiplying both sides by x minus 4, x squared minus 4 rather, I would see that the x squared minus 4 is dropped here, leaving me with 4x. And if I multiply the right side by x squared minus 4, I'm left with 0. Solving for x, we see that our x-intercept is 0. Hence, the origin is the x-intercept. It's also the y-intercept. All right. Any vertical asymptotes? By the way, I like to abbreviate the words vertical asymptote as VA. Vertical asymptotes. Notice the degree of my numerator is 1, but degree of my denominator is 2. Since the degree of the numerator is less than the degree of the denominator, what would be the wait a minute here. I'm trying to find a vertical asymptote. I do apologize. I'm jumping ahead of myself. That's how you'd find a horizontal asymptote. We'll do that in a second. To find the vertical asymptote, we set our denominator equal to what? 0. And then we have to solve this equation. Solving this quadratic equation by adding 4 to both sides and using the square root method. Take the square root of both sides. Don't forget the plus or minus square root of the number side. We can see that we have 2 vertical asymptotes. One at x equals positive 2 and one at x equals negative 2. 2 vertical asymptotes. So these are the equations of your vertical asymptotes. Finally, horizontal asymptote. Does my function have one? Horizontal asymptote from now on is going to be abbreviated as HA. Horizontal asymptote. Let's see. The degree of my numerator is less than the degree of my denominator. Therefore, the equation of my horizontal asymptote is the x-axis, which is y equals 0. That is the equation of the x-axis. That's my horizontal asymptote. Okay. I'm going to take a piece of graphing paper and I'm going to plot what I know. What have I discovered so far? Well, my y-intercept and x-intercept are the origin. My vertical asymptotes are at positive and -2. So I'm going to take a ruler here and I'm going to put vertical dashed lines through -2. And through +2. These are my vertical asymptotes. Horizontal asymptote is the x-axis. So I'm going to highlight the x-axis with a vertical hatching, if you will. That is my horizontal asymptote. All righty. So I've located my asymptotes for my graph. Does my graph cross the horizontal asymptote, which is the x-axis? Well, to determine that, you would set f of x equal to 0. But wait a minute, didn't I already do that? Sure, I did. I set f of x equal to 0 to find my x-intercept, and it's at 0, 0. 0, 0 is the point of intersection between the graph and the horizontal and the horizontal asymptote. Okay, that's where the graph's going to intersect. The horizontal asymptote is at 0, 0 there. All right. All right. Now, another thing, ladies and gentlemen. What intervals, okay, would we have to compute a point for? Well, again, intervals are defined by your vertical asymptotes and the x-intercepts. So we have this interval here. We have this interval between the vertical asymptote and my x-intercept right here. I have this interval between my x-intercept and the vertical asymptote here. And I have this interval out here. Okay. So we got all these intervals to analyze here. And let's see if we can find out how our function is behaving here. So I have this interval here. Can you give me something less than -2? Maybe -3. So let's let x be equal to -3. And let's evaluate our function at -3. That's to say we would have 4 times -3 over -3 squared minus 4, which is -12 over 9 minus 4, which is 5. So we would have -12 fifths, which is to say we would have -2 2/5. So therefore we have the point -3, -2 2/5. I'm going to plot that point in this interval here. -3 and -2 2/5 is going to be right about here. Now give me a value between -2 and 0. The vertical asymptote and the x-intercept. How about -1? Let x be equal to -1. Evaluate your rational function at -1, which is going to be 4 times -1 over -1 squared minus 4. That's going to be -4 over 1 minus 4, which is going to be -3, which is going to be 4/3. So we have the point -1 and 1 1/3. Plotting the point, -1, 1 1/3, going to be right about here. Give me something between the x-intercept 0 and this vertical asymptote of +2. How about x equals +1? Put +1 into your function. So f of 1 is going to be 4 times 1 over 1 squared minus 4, which is going to be 4 over -3, which is going to be -1 1/3. So we have the point 1, -1 1/3, that would lie in this little interval here. So plotting the point, 1, -1 1/3 would be right here. Finally, give me some x value that's greater than 2, maybe like 3 or something. Let's evaluate a rational function at 3, which is 4 times 3 over 3 squared minus 4. which is going to be 12 over 9 minus 4, which is going to be 12 over 5. So we're going to have another point on our graph, which is going to be 3, and 12/5 is really 2 and 2/5. Plotting the point 3 and 2 and 2/5. 1, 2, 3, 1, 2, and 2/5 is right here. Now we can sketch our graph. All right. To the left of this vertical asymptote, x equals -2. I know that as x approaches negative infinity, this graph has to approach the x-axis from below. It has no choice. It cannot cross it. As we allow x to approach -2 from the left, the graph has to dive down to negative infinity. It has no choice. It's got to go down like that. Okay, going in between this vertical asymptote and the x-intercept, notice I have a point up here. So as x approaches -2 from the right, my graph has to blow up towards positive infinity and become asymptotic with respect to that. The graph has to come down and it has no choice. How do I know my graph has to cross the x-axis at the origin? How do I know it doesn't, touch the origin and then bounce back up? How do we know that? Because we found a point on this interval from 0 to 2, which is below the x-axis. That's why it's important to find these points here, on these intervals here. So we had how many intervals to analyze? From negative infinity up to -2, from -2 to 0, 0 to 2, and 2 to infinity. We had those intervals to find at least one point on. So since this point's down here, my graph has got to go through the origin, and it has to pick up this point, and then it has to, as x approaches +2 from the left, it has to become asymptotic with respect to this vertical asymptote. It has no choice. Going on the other side of the graph, we know that there's a point on our graph up here because we found it when we put 3 into our function for this last interval to the right. And therefore our graph, as x approaches 2 from the right, f of x would be going up to positive infinity. And as x approaches positive infinity, the graph has to dive down and become asymptotic with respect to this horizontal axis, this horizontal asymptote. And there you would have your graph, ladies and gentlemen, of that rational function. Everybody understand the analysis that we poured into it to derive the graph? We found the intercepts, vertical, horizontal asymptotes. We computed at least one point in each of the intervals that are defined by the vertical asymptotes and also the x-intercept. So we had to analyze this interval here, that interval, this interval here to here, and this interval here to here, and then finally this interval out here. So we had to find one point in this interval, one point in this interval, one point in this interval, and one point in that interval. And that's basically, in a nutshell, how you graph rational functions, is by going through that regiment. Okay? By going through that regiment there. All right, and this is basically example 8. I just did example 8 for you. All right, but ladies and gentlemen, if you did not get all of example 8, it's right here. All right, this walks you through exactly what I just got done doing. And it shows you how the intervals are defined by the vertical asymptotes and the x-intercept. And it shows you the points that were computed. At least one point was computed in each of those intervals to ultimately then graph your rational function, which would be this guy right here. Okay. All right, so, and I want you guys to look over example 9. Just make a note that outside of class, I want you to study over example 9 on your time. I want you to convince yourself that the graph of that rational function, when all is said and done, is going to be this guy right here. Make sure you walk through that example. Walk through it. In fact, don't peek at the graph, ladies and gentlemen. Pretend you never seen the graph. Walk through it on a separate piece of paper and see if you can graph this, and then compare your answer with what they have down here when you get done. Okay? Make sure you can walk through this entire gamut here. All right? All right, and then also example 10. I want you to look at example 10. Notice this one possesses a slant asymptote because the numerator degree exceeds that of the denominator exactly by 1. So there will be a slant asymptote. I want you to study over that example. Okay, make sure you study over this example. Notice the interval they're establishing based on the x-intercepts, the vertical asymptotes, and also the x-intercepts, and there you go. Make sure you understand how they're establishing these intervals and computing at least 1 point in each interval to help you understand how the graph's going to behave throughout. All right. All right, and maybe try to do this one. You know, these skill practice problems give you extra practice. You know, maybe you can try to graph these walking through the entire gamut and then check your answer here. So there's extra practice whenever they say skill practice here. I would definitely do those. Do those on your, you know, do those individually. You notice this graph for skill practice 9 actually crosses the horizontal asymptote at this point. And to find that place where it would cross, you would literally set your rational function equal to +4, because the horizontal asymptote would be y equals 4 over 1, or y equals 4. So you set this equal to 4 and solve for x, you'll discover that this point is the point of intersection between the graph and the horizontal asymptote. All right, so I am done with that section there. Please do study over those examples that I mentioned. I wish I had time to go over them all, but I just don't. I still have one more section that I have to cover. So section 3.6 will wrap things up today. And it is entitled Solving Polynomial and Rational Inequalities. So 3.6. All right, so section 3.6, solving rational and polynomial inequalities. Now, these are not equations, they're inequalities. All right, let's just dive right in. The best way to learn how to do this is to just start looking at problems here. So here we go. We're going to solve this polynomial inequality. We got 3x times x minus 1 is greater than 10 minus 2x. This is called a polynomial inequality, and we want to solve for its solution set here. To do that, I have no choice, but I'm going to have to distribute here. So I have 3x squared minus 3x greater than 10 minus 2x. So what we really got going on here is called a quadratic inequality. I'm going to zero this inequality out. You always want to get these things zeroed out, with 0 on one side. So to do that, I'm going to add 2x to both sides. And I'm also going to subtract 10 from both sides. The left side becomes 3x squared. Negative 3x plus 2x is minus 1x. And then I got minus 10. And that's going to be greater than, the whole right side goes to 0. This drops out and that drops out, and we're left with 0 here. Now, what we have to do is, now that we have 0 on one side of our inequality, I'm going to factor the non-zero side completely. We must factor this trinomial. Quick check, does it factor? We better hope so. 3 times negative 10 is negative 30. Are there two factors of negative 30 that do exist that add up to negative 1? They do. Negative 6 and 5 would fit the bill. Therefore, this trinomial will factor. I'm not going to go through the grouping or the trial and error method to factor it. The bottom line is we have to get this thing factored. So we'll have a 3x here and an x here. And so what else are we going to have over here? I'll have the minus 2 here and the plus 5 here. I think that factors correctly. 3x squared minus 6x plus 5x is minus 1x, and 5 times negative 2 is negative 10. All right, now the next step is we're going to have to find what are called critical numbers. Some textbooks refer to these as significant numbers or critical numbers. I like to call them critical numbers here. But don't confuse these with what you would call critical numbers in Calculus 1. They take on a different meaning in Calc 1. So maybe you could call these significant numbers instead of critical numbers. Anyways, those are going to be the numbers that send these factors to a value of 0. So we take both factors, set them equal to 0, and solve for x. Here we get negative 5/3. Setting our second factor, x minus 2 equal to 0, solving for x, we get x equals positive 2. So what these numbers are going to do is they're going to partition our number line up into different intervals that need to be tested out with our polynomial inequality. So I got negative 5/3 and I have positive 2. I have three intervals that I have to test out to see which interval or intervals produce solutions to this polynomial inequality. We're going to test out three intervals. Interval number one. Can anybody give me a nice real number that's less than -5/3? What is -5/3? Isn't -5/3 as a mixed number really negative what? 1 2/3? Can somebody give me a real number less than -1 2/3? Some nice number.
-2.
Let's look at -2. Therefore, letting x be -2, let's put -2 in here and here into our quadratic inequality and see if -2 is a solution. So is 3 times -2 plus 5 times -2 minus 2, is that greater than 0? Well, this gives you -6, and -6 plus 5 is going to be a -1, and this is going to be -4. Is -1 times -4, which is 4, is that greater than 0? Is that true or false? That's true, isn't it? So it looks like this first interval will produce solutions. I like to write the word true. True in my mind indicates that this interval does produce solutions to my quadratic inequality or my polynomial inequality. Now, your author is using his jazz here, whereby they're showing the signs of each of these factors in each of these intervals, and they're arguing why this interval would produce solutions. You don't need to go through all that technicality stuff. I mean, you can just say, yes, this interval will produce solutions. All right, can you give me a nice value in interval number 2 between -1 2/3 and +2 that we can test out? Give me a nice value. Something nice. What's the nicest value between these values here?
0.
0 would be the nicest value to work with. Therefore, take 0, substitute in here and here, and verify, is 0 a solution to this inequality? Is 3 times 0 plus 5 times 0 minus 2, is that greater than 0? True or false? Well, this is 5 and this is -2. Is 5 times -2, which is -10, is that greater than 0? Is -10 greater than 0? False. No solutions are going to come from this middle interval. Give me something greater than 2. Some nice value bigger than +2 in this third interval here.
3.
Let x be 3. Put 3 into your polynomial inequality. Verify, is it a solution? So is 3 times 3 plus 5 times 3 minus 2 greater than 0? Does that work? Does that work? Well, let's see here. This is going to be 9 plus 5 is 14 times 3 minus 2 is 1. Is 14 greater than 0? The answer is yes. So we say true. We're ready to form our solution set. Therefore, ladies and gentlemen, it's all the intervals that are marked true that will provide solutions to our polynomial inequality. Notice I don't have the equal sign as part of our inequality, just a strict inequality here. Therefore, we do not include these endpoints. So this is the graph of my solution set. Open a closed parenthesis on -5/3, and we shade to the left. Open parenthesis on 2, shade to the right. Interval notation, what would be my solution set? Well, the solution set's going to be from -infinity up to -5/3, but not including -5/3 in union with, not including 2 up to +infinity. This is your solution set. In interval notation, this is the graph of the solution set for this polynomial inequality. As long as you choose a number in this interval or this interval, it will be a solution to this inequality. There will be no solutions coming in between -5/3 and 2. No numbers satisfy this inequality. Questions how we solve that polynomial inequality algebraically. We solved it algebraically. Okay. We solved it algebraically. Now, ladies and gentlemen, could we have solved this quadratic polynomial graphically? The answer is yes. We could have solved it graphically. Here's how we could have done it. We could have literally have graphed the left side of this inequality, which is a quadratic function. So its graph would be a parabola. Would this parabola open upwards or downwards? It's going to open upwards. right? Leading coefficient's positive. If you were to sketch the graph of this polynomial, the graph would be this parabola that opens upwards. And notice its x-intercepts are precisely what I've been calling the critical numbers, which are -5/3 and 2 are the x-intercepts. -1 and 2/3, +2. Now, you know what your solution set's going to be? Your solution set is going to be a set of all real numbers for which the graph of this quadratic function is going to be greater than 0. The solutions to this polynomial inequality are going to be all values of x for which the graph of this quadratic function is going to be above the x-axis. Why above the x-axis? Because it's above the x-axis, ladies and gentlemen, your y-coordinates are what? Greater than 0. Do you agree? Positive. Greater than 0. So you know what? Graphically, you could solve this polynomial inequality because you can see that it's only on the intervals from -infinity up to, but not including -1 and 2/3. It's on this interval that the graph is above the x-axis. It's right in here where y is greater than 0. It's also true for +2 to +infinity, where your graph is above the x-axis, because it's in here where y is also greater than 0. That's how you can graphically solve that polynomial inequality. The graphical solution. Everybody understand it? There's no solutions that come out of this interval in between -5/3 and 2, because in this interval, the graph is below the x-axis, which means in here, y is less than 0. Our y had to be what? Greater than 0. Is that making sense? How graphically you can solve these polynomial inequalities just by graphing the polynomial and looking and seeing where the graph is above or below the x-axis. The graph is above the x-axis where y is greater than 0, and the graph is below the x-axis when y is less than 0. Okay? So you can always check your answer using your graphing calculator if you want. You can always check your answer using your graphing calculator. All right, well, that wasn't too bad. Maybe we could solve another one. Hold on a second. Time check. 3:56. Okay, we're getting behind the 8 ball, but I think we'll have enough time just to finish. All right, maybe we should try another one. How about that? Solve -x² plus x plus 12 is greater than or equal to 0. We want to solve this polynomial, or specifically this quadratic inequality. Okay. Well, how to do that? Well, first of all, we want to get 0 on one side. Well, we're lucky. We already have 0 on one side. Next step. Next step is to completely factor this left side. But you know what I don't like? I don't like this leading negative side. That looks messy. I'd like to get rid of it. How could I get rid of this leading negative sign? Anybody? How can I get rid of this leading negative sign and still have the same equivalent inequality?
Factor out a negative sign?
We could
Or
factor
times everything by negative.
Yeah, I'll tell you what, let's multiply both sides of this inequality by a -1. That'll force a +1 in front of x². Easy thing to do. When you multiply both sides of or multiply a polynomial by a negative, the effect it has is just to toggle the signs of all the terms. Now, got to be careful here. Whoops, almost made a mistake. When you multiply both sides of an inequality or divide both sides of an inequality by a negative, what do you got to do with your sign, your inequality symbol? Remember? Because I'm multiplying both sides of this inequality by a negative number, I have to flip my inequality symbol around. Yep, don't forget that. Got to flip the symbol around. So therefore, distributing the negative throughout, we'll have +x² minus x minus 12 is less than or equal to 0. This polynomial inequality is equivalent to this one. Okay. Now we'll try to factor this easy type of trinomial here on the left. I need two factors of -12 that sum up to the middle coefficient of -1. What would they be? After some thought, -4 and 3. Therefore, this trinomial factors immediately in x minus 4 times x plus 3. Left side is completely factored. And now, ladies and gentlemen, it's time to find what I've been calling critical numbers. Again, some textbooks refer to them as significant numbers. Bottom line is they are numbers that are going to set these factors equal to 0. So therefore, we set the factors equal to 0 and solve these equations And therefore we get x equals 4 as being a critical number and x equals -3. These numbers are going to partition my number line up now into disjoint intervals that will need to be tested. So -3 and +4. I now have how many intervals to test? Interval number 1, interval number 2, interval number 3. So I got to test these intervals out. Okay, can somebody give me a nice real number out of interval number 1, something less than -3? Something less than -3. Nice value. How about -4? Put -4 in here and verify. Is -4 a solution to this inequality? This is going to be -8. This is going to be -1. Multiplying these together, you get +8. Is 8 less than or equal to 0? That's false. False. No solutions come from this interval. How about give me a nice value between -3 and 4? Interval number 2. How about x equals 0? Put in 0 here and here. Is 0 a solution to my inequality? Well, I get -12 when all is said and done here. And -12, is that less than or equal to 0? That's true. Finally, interval number 3. Give me something nice that's greater than 4. I'll say 5. Put 5 in here and here. Is 5 a solution? This gives me 1 times 8, which is 8. Is 8 less than or equal to 0? The answer is no. False. I have a question for you, ladies and gentlemen. Would I include -3 and 4? Yes or no? Anybody? Would I include -3 and 4?
Yes.
Yes, because now my inequality allows for the fact for this polynomial to be equal to 0. And it's at -3 where the polynomial is equal to 0, and also at +4 where the polynomial is equal to 0. You must use brackets, therefore, to include these values. And then we shade in between. You are looking at the graph of the solution set, this quadratic inequality. Interval notationally, it's all the real numbers between -3 and 4, including endpoints. And we're done. Questions, how we solve this quadratic inequality algebraically. Okay, algebraically. All right. If you were to take the time maybe and solve it graphically, you would have to graph this quadratic function here. And it would be a parabola. Would this parabola open upwards or downwards? Upwards or downwards? It would open downwards, and its x-intercepts would be -3 and 4, correct? So if you were to take the time to, just sketch the graph of this thing, you're going to have 4 out here, you're going to have -3 out here, and the vertex point would be, well, the x-coordinate of the vertex point is -b/2a. Remember that? Which is going to be -1/2 times -1, which is going to be 1/2. So the vertex point occurs at 1/2 here. So it's going to be like up here. Bottom line is the parabola is going to open downwards. It's going to go through these x-intercepts here. And ladies and gentlemen, we're interested where f of x is what? Greater than or equal to 0. Do you agree? Notice, I graphed this one. See, I graphed this. And it said this had to be greater than or equal to 0. So this f of x right here, which is this is the graph of this, must be greater than or equal to 0. That only occurs where y is greater than or equal to 0. Well, where must the graph be for y to be greater than or equal to 0? The graph has to be above or below the x-axis. What would be the case? For y to be greater than or equal to 0, the graph has to be above the x-axis. And you can see that only occurs in this middle interval here from -3 to 4. It's on this interval where the graph is above the x-axis. It's in here, this interval here, where y is greater than or equal to 0. If you go in this interval below -3, the graph is below the x-axis, meaning down here y is less than 0. Or if you go above 4, the graph is below the x-axis where y is less than 0. It's only in between -3 and 4 where y is greater than or equal to 0, where f of x is greater than or equal to 0, where f of x is greater than or equal to 0. Do we understand the graphical interpretation of the solution set? All right, I only have time, it looks like, to show you how to solve a couple of rational inequalities now. I showed you how to solve some polynomial inequalities algebraically and also maybe to check your answer graphically. Now, ladies and gentlemen, let's close the door here on today's session by showing you how to solve a couple of rational inequalities. All right, here is a rational, it's called a rational inequality. It's called a rational inequality because it's a rational expression and an inequality. We call that a rational inequality. So I'm going to show you how to solve a classic rational inequality. We want to solve this for its solution set X. To do that, first we want to get 0 on one side of our inequality, just like we did with polynomial inequality. So I'm going to subtract 3 from both sides. When I do that, the right side will go to 0. Now I have to get a common denominator to subtract 3 from this rational expression. Now this 3 really sits over what? 1, understood, correct? So what would be my least common denominator here of 1 and x minus 2? Least common denominator would be x minus 2. This fraction already has a least common denominator. We don't have to do anything to it. But this 3 over 1 needs help. In fact, the denominator here has to be multiplied by x minus 2. So we got to multiply the numerator by x minus 2 also to build up 3 over 1 into an equivalent fraction that now has the least common denominator. So now both of these have the same denominator, in which case, being the case, I can begin to, I can put them together as one fraction now, and then I can simplify my numerator, distributing -3 in here. Combining like terms in the numerator, I get x plus 1 over x minus 2 is less than or equal to 0. And now, ladies and gentlemen, I need to find what are called critical numbers. Critical numbers are numbers that send any factor in the numerator and the denominator to 0. So x plus 1, set it equal to 0, solve for x. So x equals -1 is a critical number. X minus 2 in the denominator, set it equal to 0, solve for x. So x equals 2 is another critical number. These critical numbers are going to partition my number line up into intervals that need to be tested to see which ones yield solutions to my rational inequality. So here we go. Put those critical numbers on your number line. And now we have 3 intervals to test out. Interval number 1, 2, and 3. Interval number 1, give me something less than -1. How about -2? Put -2 in here and here. See if it's a solution to this rational inequality. Hence, I get -1 over -4, which is 1/4. And is 1/4 less than or equal to 0? Is that true or false? That, ladies and gentlemen, is false. No solutions are coming out of this interval for this rational inequality. Interval number 2, give me something in between -1 and 2. The nicest number to work with is 0. Put 0 in here and here. Verify. Is 0 a solution to this rational inequality? Is 0 plus 1 over 0 minus 2, which is -1/2, is that less than or equal to 0? Is this true or false? That's true, isn't it? True. Finally, give me a real number greater than 2 in interval number 3. Something nice like 3. Put 3 in here and verify. Is 3 a solution to this rational inequality? Is 4 over 1 less than or equal to 0? That's false. No solutions come out of here. One last thing. Would I include -1? Careful. Would I include -1? Is -1 a solution of this inequality here? You can let x be equal to -1 and verify. Put -1 in here and here. What happens when you put -1 in? You get 0 over -3, which is what? 0. Is 0 less than or equal to 0? Is that true or false?
True.
That's true. You must include -1. Bracket on -1. Would you include 2? Put 2 in here and verify. Why is 2 not going to work? Because the denominator goes to 0, doesn't it? And 3 divided by 0 is undefined. Undefined. Do not include 2. Parenthesis on 2. Shade in between them. You have the graph of the solution set to this rational inequality here. Interval notationally, the solution set is including -1 up to, but not including 2. There's your answer in interval notation. Do we understand, ladies and gentlemen, how I solve this rational inequality algebraically? Okay. Now, to solve this graphically, you would have to graph this rational function, and you'd have to look at and see on what intervals the graph is below the x-axis, because this has to be less than or equal to 0. So the intervals in which the graph of this rational function is below the x-axis would be the solution set to this rational inequality. I'll bet dollars to donuts that the graph is below the x-axis on this interval, okay? For values less than -1, the graph would be above the x-axis. For values greater than 2, the graph would be above the x-axis. The graph would only have to be below the x-axis in this interval, -1 to 2. And you can convince yourself just by graphing that, on the number line. I mean, we could look at that really quickly here. Ladies and gentlemen, the Desmos calculator. I love it. Desmos graphing calculator. Just type that in. Oh, I'm going to put a link on Canvas. I will do that. I keep forgetting, but it's called the Desmos graphing calculator. You can use this for other classes too, not just for this class. If you go on into calculus, this is an invaluable little handy little tool to use to graph functions so you can analyze them more easily. I'm going to type in this rational function so we can verify very quickly that the interval, or excuse me, the solution set to this rational inequality is exactly what we got. So I'm just going to type in my rational function, and let's verify. Is my graph, ladies and gentlemen, is my graph below the x-axis on the interval from -1 to 2? -1 is right here. Okay. See, -1 is right here, and +2 is right here. Do we agree on this interval from -1 to +2 on this interval on the x-axis right here, -1 to 2? It's on this interval where my graph is precisely below the x-axis. It's on this interval where y is less than 0. Why do we include -1 in our solution set? Because the graph actually has a point on it that has -1 for its x-intercept. Why do we not include 2 in our solution set? Because x equals 2 happens to be a vertical asymptote to this rational function's graph. See how it gets closer and closer to x equals 2 from the left, but it will never touch or cross that vertical asymptote. Never does. It gets infinitesimally close to it. No matter how far down you go, if you zoom in, you'll see that that graph never touches x equals 2. You see that? It never touched x equals 2. Getting closer and closer, but it never will ever touch it. Oh, excuse me. All right. So that hold on a second. And therefore, that kind of like cooperates with our algebraic solution here. Do you agree? I think I swallowed a dragonfly. No, I'm just kidding. But that is that one there. All right, ladies and gentlemen, I'll show you maybe one more, and then we'll cut it loose. 414. I have just enough time just to sneak another one in here. I'd rather show you this last one rather than have you do a classwork, because this one here is a little bit, it gives you a different look, a little bit. And I just want to walk ourselves through it quickly here. First thing I got to do is zero this thing out. So I'm going to drag this whole rational expression over to the left side by subtracting it from both sides. So I minus off 6 over 1 minus x. And now we have 0 on one side. Now I got to get a common denominator so I can combine these into one fraction. Least common denominator of 4 minus x and 1 minus x is going to be 4 minus x times 1 minus x. You got to have both these here. First fraction's got the 4 minus x. It's missing the 1 minus x. So the top and bottom of this first fraction gets multiplied by 1 minus x. Second fraction's got the 1 minus x. It's missing the 4 minus x. So top and bottom of it gets multiplied by 4 minus x. Now that we have a common denominator, we can look at begin to work on our numerators here. I'm going to distribute here. So we'll have 3 minus 3x. Distributing, look at this, careful here. I'm distributing a negative 6. Negative 6. So that's minus 24. That's positive 6x. Don't mess these signs up. That'll kill the problem. Combining like terms in the numerator, the negative 3x plus 6x nets us 3x. 3 minus 24 is minus 21, all over our common denominator. Factoring a 3 out of the numerator, out of both terms, leaves behind this. Now it's time to find critical numbers. Critical numbers are numbers that send your variable factors in the numerator and denominator to 0. So set x minus 7 equal to 0. One critical number is 7. Set 4 minus x equal to 0. Solve for x. Another critical number is 4. Set 1 minus x equal to 0. Solve for x. Another critical number is 1. These are your critical numbers. Therefore, we need to test out all of these intervals here. So put these critical numbers on your number line here. And in this case, we have how many intervals that need to be tested? Not 1, not 2, not 3, but 4 intervals. I got to test out 4 intervals. Interval number 1, give me something less than 0. How about x equals 0? Take 0, ladies on, plug it in here, here, and here. Here, here, and here. Is 0 a solution to this thing? Well, this is going to be negative 21 over 4. It is a negative. I don't really care to simplify that anymore. Is a negative less than or equal to 0? Is a negative number less than or equal to 0? That's always true. Interval number 2. Give me something between 1 and 4. Let x be equal to 2, maybe. Put 2 in here, here, and here, and verify is 2 a solution. Minus 2. 1 minus 2. So this gives me, it's got to be negative, that's going to be negative 15. And this is going to be what? 2 times negative 1, which is negative 2. This is going to be a positive 15 halves. Is a positive less than or equal to 0? The answer is false. Interval number 3, give me something between 4 and 7. How about 5? Put 5 in here, here, and here, and verify. Here, 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 and here, and verify. This gives me negative 2, this gives me negative 6 in the numerator. This is negative 1 times negative 4 is 4. It's a negative. Is a negative number less than or equal to 0? True. Finally, interval number 4, give me something bigger than 7. like 8. Put in 8 here, here, and here, and verify. This gives me 3 times 1 is 3. Downstairs, I got a -4 times a -7 will be a positive 28. Is a positive less than or equal to 0? That is false. Finally, would I include 1? If you put 1 in for X here, here, and here, what does this thing do? What happens to it? If I put 1 into this factor becomes 0. The whole thing's undefined. You're dividing by 0. Cannot include 1. Do I include 4? If you put 4 in here, here, and here, this factor goes to 0. The denominator zeroes out. You cannot divide by 0. Undefined. Do not include 4. If I put 7 in for X here, here, and here, the denominator doesn't become 0, but the numerator becomes 0. Is 0 less than or equal to itself 0? The answer is true. Include 7. Bracket. Solution set. Interval notation is from -infinity up to 1, but not including 1, in union with, not including 4, up to 7 and including 7. Done. That's the solution set, ladies and gentlemen. And interval notation. That is the graph. And therefore, that is the solution set of this rational inequality. I'm out of time. I hope you enjoyed this lecture and got something out of it. We covered a lot of ground tonight. Okay, 3.5 and 3.6. And I will open up the sections in Alex so you get going on those. If you have any other questions, I'll stay on the line. Other than that, you have a great Halloween. Have a safe Halloween. And hopefully I'll see you next month, ladies and gentlemen. All right. Take care.